Guys, welcome back to my YouTube, Twitter, TikTok streams. So today's live stream is basically a re a redo of a previous stream I did, I think about 2 weeks ago. Um, yeah, so today I'm going to basically be redoing that stream, and I'm going to be doing it as concise and as straight to the point as possible, which is something I did not do in the last stream. So, guys, please, if you can hear me, please consider um, leaving a comment for me in the comment section. At least that would help me know that I'm speaking to people and not just bots. Um, but today's live stream, basically, I'm going to mainly focus on. Uh, okay, I think this is better. Yeah, so I'm going to talk about generics, which is something that I initially covered in my previous streams. But today I would be looking at it again. So the purpose of this is I felt the other one that I had done wasn't really up to par. So there's a need for me to like redo it, right? Um, yeah. So um, if you take a look at my screen, you would see that I already have code from the previous live stream, basically around generics in Rust. So if you've been to my previous streams, you would know that I usually create a file and I import it into the file where I make it a public file or a module. I mean, in Rust, everything is a module at the end of the day. And then I import it into the main, right? So we have all our previous covered topics imported into the main, from constant types to variable bindings down to generics. So without further ado, and then without wasting much time, so what I would do is I will just go ahead and completely delete everything I have here from our previous stream, and we'll just start again from scratch. So, guys, once again, welcome back to my live streams. I've not been active for about a week, or let me say 2 weeks. Life happened, so I couldn't make it to stream in those weekends, right? I couldn't make it to stream in those weekends because I had some other engagements and stuff I had to, um, you know, deal. So, guys, please, if you can hear me, please consider leaving a comment. In the chat box. There's a chat box, right? Whether you're on Twitter or YouTube or I think TikTok. This should also be streaming on TikTok. I've not checked, but you should be able to see and drop a comment and let me know if you can hear me. Um, so once again, welcome to the live stream. So okay, let me. Somehow my screen stopped sharing. Okay. All right. So we are back again. We are back again. So today we're going to be talking about generics. Um, Basically, we are going to try as much as possible to master the concept of generics in Rust. Yeah, we're going to try as much as possible to master that concept. Basically, generics allows you to write code. Basically, code that is function types, traits that can work with any data types, right? If you've followed my previous lectures or videos, you would see that we use, Rust is very explicit, right? So if I go into, for instance, let me say, um, this is the expression. When we did something about expression, let me look for an example. So if you take a look at line 58, where we did some kind of stuff here, you can see that we passed an integer, and we have this kind of implicit, type passed here for us. At least I think by the Rust Analyzer package or two that I use on VS Code, right? So today we are going to be looking at how we can generically, right, use a value that would accept any data type that we pass here, be it integer, float, string, or boolean, right? And we're going to be looking at that. Yeah, so that's basically what this whole thing is about, right? So what this helps us to do is that it leads to lesser code duplication and a greater flexibility in our code, right? Another thing to take note of is that Rust generics is strictly type safe, and thereby ensuring that your code works correctly and efficiently, right? So there are two things that makes the whole Rust generic. There are two things that makes it special. You know, one of them is that there is no runtime overhead, right? So the Rust generic is monomorphic, and what I mean by monomorphic is that there is no unnecessary runtime cost to using generics in Rust. The second one is type safety, which I've mentioned before. They ensure types are strictly ahead to, avoiding any runtime errors that could occur in a less type safe language, or languages like maybe JavaScript or Python and the rest. Yeah. All right. Thank you. Thank you. All right. So now, so today we are going to the first thing we're going to look at is understanding, um, parameters, and how they work generally, right? So I'm going to define a function, and this function is going to take a generic type, and this generic type can be anything, right? So it's going to take a generic type, and then I'll explain from there, right? So first off, write a function. So let's say, okay, sorry, adjust my mic very well. All right, yeah. So the first thing we are going to look at, I'm going to add a comment here. I'm just going to say understanding type params, right? So that type params is short for parameter. So first off, we are going to look at a very simple example using a function, right? Which is like very simple. We've always been writing functions in our previous live streams. So I'm going to use a function to demonstrate this. So first off, I'll create a function called foo. And this function, so I'll just go ahead and write it out and explain what's happening here. Okay, so believe it or not, we've created a function, a generic function, right? So in this generic function, you can see we have t. Let me zoom this in and close this out since I'm not using it. So we have this t here, right? So this t is the type parameter. So what it does is that it acts as a placeholder, right? It acts as a placeholder for any type at all. So foo here, foo is the name of the function. It's just a dummy function. In Rust, we use this angle brackets, so the less than and greater than signs, kind of like angle brackets to indicate a generic type, which is what we have done here. Right? Then we passed it as an argument, as we would always do in every other, um, Rust, code, right? Right. So basically, this here, this angle brackets with a T in it, represents our generic type. Take note that the T is basically a Rust convention. It's not like, it's not a must that you must use T. I can change this to any alphabet of my choice. I can decide to use A. So if I do that, that means what I will pass here as the argument has to be A, right? So this would still work, but based on convention and what you would see in other code bases and stuff, it's always going to be T, right? So just follow the convention. There's no need of doing something entirely different. Good. Now let's move over to, so now we've created a function. So in order to hide these errors, let me see. Use variable args. Okay, sorry. I don't want any error. in any warning and stuff. So I just pass an underscore there. Um, so an underscore at the front. Let me see if that will work for the function too. Yeah. So because I don't want all the warnings from Rust and stuff telling me that I've not used this function, so I just passed an underscore to kind of make it silent. So now let's see how we can also, like, structs are very common in Rust, right? They are very, very common. Let's see how we can also, create a generic struct. So struct is short for structures, in case you're not familiar with that. So um, let's call this struct, and then here generic function, and generic structs. Okay. So now, in order for us to create a struct, we use the struct keyword. So struct, and we'll just call this a single. I'll call it single gen. And once again, we'll pass the angle brackets, pass our T, so it has to be capital letter. And we'll just pass the tuple with the this thing there. So we have to also pass our semicolon at the end. Yeah. So now we've created a generic struct, right? In our previous streams, right? We've created generics in the past, right? So if I even go back to some of our codes, I can see. So you can see if I continue looking, so you can see that this is a struct, right? This is a public struct. This is a public struct. A struct. You just have to focus on this part. Is a book, right? You can see but it's public, in the library module and stuff, right? So we've done this in the past, right? So it's not like it's something new. So we just created a generic struct, and we're now going to look at how we can instantiate and use this struct, right? So we can init this struct with any type, right? So the first thing we're going to initialize this struct with a character type, right? So we say let's just call it char, and we are going to now write single gen, and we'll pass a character type of, let's just say, S here. So we need this, right? Also, we're going to pass another type. So let's say an I32, I32. Okay. I'll say single gen. So instead of passing an I32 there, we'll just pass a number. We'll call it, let's say, pass it here. Okay. Yeah, so this mic is kind of blocking me. So it's saying expected item found keyword let's for the full list of items that can appear in the module doc, blah blah blah. What's this guy saying? Okay. Right. Hmm. Okay. Found no, I'm having this error. So it says consider using static or const instead of let's. Okay. Or static. Expected item found keyword lets for the full list of items that can appear in modules. Okay, see, blah blah blah. Whether using static or const instead of lets. Never experienced this kind of expected an item. Okay, straws. This out here. Okay, so all right, so basically what I'm trying to do here, I don't understand why I'm having this error. I must be missing something that I'm not seeing. Close all this, not using them. Okay, let me see type of you don't have to. It should still work under normal circumstances. Okay. It should still work. Okay. So this always so I think I would basically have to wrap this in a function instead of letting it to run on its own. So I guess the reason it's telling me to make it a static is because I think it's in the global scope, right? And it cannot appear in a module, and we know that a file in Rust is all things in Rust are module. Like a file in Rust is a file, yeah, is a module, right? We can also make a specific section of the code a module if we add the mod keyword to it. And we already did this, right, by importing it into the lib folder and stuff. So I think to solve this or to resolve this issue, I have to wrap it in a function. So I will just create or I will just make it static, right? So let's just make it static and move on instead of trying to, right? Let's just make it static and move on instead of trying to, oh no, let's make it a function. Let's create a function and wrap it in that function. So I would say function generic. Okay. Pub generics, and in that function I'm not just going to return anything, just pass these two guys in there, right? Okay, so save. Yeah, so that error should be gone exactly. Yeah, so that should fix our issue. And this expected item found the keyword let's after the full list of okay, unused variables. Okay, yeah. Yeah, so sorry about that. So I kind of forgot that this whole thing was in the global scope, right? And we can't use lets in the global scope unless it's wrapped in a function. Little things like this, little things. But yeah, then as you can see, we are using this guy, so the single gen, and we are using it. We are passing a character type, so you can see there is an implicit type, inference here. So we have single gen, which is our structure, and it takes a character type, right? And we also have that same single gen that is taking an integer type of I32, right? So in order to hide this unused variable of character type and unused variable of integer type, we'll do same thing that we did here. We added the underscore. So we'll do that here. So once we do that, it should go away. So save this and can go check runs. Um, yeah, so now we have like a clean um, you know, workspace. So you can see how we can even go ahead to like say, let's bool. So that is a boolean. It's going to be single gen, and I'll pass true to it, right? So you see there will be an implicit um, there will be an implicit return. So once I save this, okay, where's this person? All right. All right. Single, not single. Single. All right. So there was a little typo there. So you can already see that this is a type of boolean, right? So a boolean type that we have here. All right. So now let's go ahead and look at how we can work with like how functions and generics can work together. So basically, when defining functions that work with generics, Rust allows us to specify the type when calling the function. So if like it allows us to specify the type when calling the function if it's necessary. So let's look at some examples with a generic function that works with a generic struct um, that we would call sgen. So we'll create a struct. So let's say no need of making this guy public. So let's create a struct called sgen. So we'll create a struct, say sgen, sgen, and this struct is a generic type and it takes just similar to what we have done before. So I would have just even copy and pasted from that other guy. So now we'll create our function. So our function is going to use this struct. So we'll create so let me add a comment here. Um working with functions and generics. Okay, so we've created our struct. So now let's create a function that will make use of our struct. So we'll say fn. So a very simple function. And we'll call it generic 2. And this guy is generic function, so it takes the angle bracket and the t, which is a placeholder. Then we'll pass an argument, right? Similar to what we had done before. So here we'll just call it s, and we'll then pass our struct, which is sgen. Sgen. So pass the placeholder. Don't forget to do that. And basically that's it. So what's the difference here? The difference here is that we are passing this our struct. If you take, you see, if you can take a look at how I highlighted it, and it's highlighted on line 19, we're passing it directly as an argument to this function, right? So we're passing directly as an argument to this function. So it may contain types with the structure drop view depending on the type parameter. So if you take a look at this, you will see that this is a struct. As I hover over it, so it's a struct. It's sgen, a generic type, and a placeholder, and of generic type t. So once I save this, we should have like a bunch of warnings and stuff. But I would also sanitize that. So the way we do that is by adding another underscore here and save. And I don't also want this. I don't want another underscore here. Save this. Save this. Okay. So one thing to take note of is whenever you add this underscore, right, it's like it is completely hidden even from the compiler. So that's why I have this error here saying cannot find type sgen in this scope, right? So just have to leave that, guy. So I will not have that. Or we can undo and probably also add another one here and save. So let's see if that would completely hide our warnings and errors. Okay, so the reason for that is what I still know. Okay, contain. Okay, yeah. So that has gone out completely, right? So the reason I'm adding on this underscore is because I don't want a bunch of warnings, all over. So I also do that for this guy, because I don't want that error. I don't want that warning. Oh, I can just leave it, right? It's not harming anybody, but at least let it be reduced to the barest minimum. So now, after doing that, after creating this function, so this generic function that we are using this function, we're using our struct with this function, right? Now we can like when we want to call our function that is generic true, Rust allows us to either explicitly or implicitly specify the type that we want to call, right? So guys, please hold on. I have to take this call. All right, guys. Sorry for the um I had to take that call. Okay, so as I was saying, Rust allows us to explicitly or implicitly specify our types, right? So for the sake of that, I'm just going to remove all this my underscore I've added everywhere, so that I won't have any issue when I try to use it. So now let's let's look at the implicit, sorry, explicit usage. Can't spell today. Usage, right? So here we can call the name of this our function. So we know that the name of our function is generic too. So we'll say generic underscore two, and we can then pass our double colon, and there would also we'll then go ahead and pass, because we want the type of character, right? So pass that here. So this is explicitly, we are passing it explicitly. Then we'll pass a parenthesis, then say sgen, and here we'll then pass our character. So we can just pass it. I mean, okay, so this, right? So we can do this, identify ourselves, supercrate, blah, blah, blah. Yeah, so don't mind this error, right? I know why this is happening, but for the sake of example, for the sake of this, like, example, right? We'll just go ahead with this, right? Or I can, uh, okay. Expected and identify yourself, blah, blah, blah. Okay. Um, view the problem. Hold on. Okay. Uh, hmm. Okay, so syntax error, expected an item, syntax expected an item. Hmm. Okay, expected an item. For here, what's am I getting? The character type, okay, represents validity layout, std char. Okay. This document describes a number of method traits on the character type. That should not be the issue. That should not be the issue. All right. Um, Okay. S type. Oh, I see. I think I missed this guy. Save and see. So I have to pass this whole thing. I think I still have to pass this in a function, basically, right? Because I think I have to do that. I have to pass it in the function in order for these weird errors to get away. So in order to do that, I'll take this guy, so our original generic function, and copy it to the comments. Um, so paste it here, and I'll take this guy, so explicit usage with the comments, and I'll paste it here. All right, so you can see that error is gone. It's funny. Explicit. Okay, and what am I getting? Expected identifier. Blah blah blah. Anyways, then what else? What else? Okay, so I'm going to take these comments and put it in that function so that speaks to these guys here. So I'll save this and let's see. All right, so we don't have any of those weird errors again. So you can take a look. You can see how I explicitly passed my character here, specifying that this is a character. But I mean, in a real life situation, I like, not like in a real life situation, this is actually good to do, but I won't really do this. And the reason for this is because Rust already handles that implicit, it infers it, right? The implicit type. So I'm going to give another example. So I'll call this implicit inference of the type. So I'm going to use a type of I32, right? So I'll just say generic underscore 2, and I'll just pass this. So it's good that I'm using Rust Analyzer. So it is going to practically or basically show exactly what the type that I passed is. So I'm just going to say sgen. So remember, we're passing our struct here. And here I'm going to say this sgen, I'm going to call it 38. I'm going to say 38. I'm going to pass a semicolon there, and I'm going to save. So when I save this, give it some time, and I should be able to, yeah. So now this also works, right? But there is an implicit inference. So if I hover over this, you will see that the T here is saying that the T, right, is an I32. Do you get? So if you take a look, you see it says Rust by example generics. So there's a function that takes the sgen, so the value of s. So this s, the 38 I passed in here, is going to become, is this, right? So that's happened now. Okay. So it has done that implicit inference for me. So I don't have to explicitly write this long extra layer of code, right? Not really a layer of code. I don't have to write extra in order for me to achieve this, right? So this also works. And if you take a look at this, if I hover over generics, is type of I32. If I hover over this, is a type of character. If I change this from the number to something like a boolean, so let's say true, I pass through there, and I hover over this, you see that it takes it's now T is now a type of boolean, right? So you can immediately see how I can define one struct, which is this guy, and reuse it for multiple places in my code by basically just passing generic types to it, right? So yeah, so that's it for generics and how to use it with functions and all the implicit and explicit usage. So I would usually always go with implicit, right? Because it's faster and shorter for me, right? I don't have to manually write those things by myself. So next, um let's look at, so I'm now going to go ahead and add an underscore here, because believe me, I don't like what I see. So I'm going to add an underscore here, and I'll just save. At least I can manage few of these, not all of them, for real. So I'll just do that, and let's go ahead. Now throws an error. A lot of error. Okay, consider naming it to generate to. Okay, I see. Let me just remove that. Let's leave it that way. Let's move on. So now the next thing we're going to look at is implementing method for generic types, right? So let's say so now that we've looked at how a generic function works, let's dive into implementing method for a generic type. We already know what methods are. Methods are like functions, right? But they are specific to a particular. They are implemented on. Um, they are implemented on a struct, right? They are functions that are implemented on a struct. So I would write that code and would see how it works. So let's look at what another thing again to note before I move on is that this is a very powerful feature that allows us to define behaviors, like default behaviors for structs that can work with multiple data, right? So let's look at an example. So I'll create another struct, and let's say struct. I'll call this gen val, so general value. Once again, it takes an angle, so I'll just quickly do that, right? But in this case, because I don't just want to pass t, so I'll use curly braces, and there I'm going to pass a value called gen underscore val, and this value is going to be a type of t, right? So I will move this, don't have to pass that there. The next thing I'm going to do is I'm now going to write an implementation on the gen val, and also write the method, which is a function. So this function, we're going to call it value. We're going to write that function on the gen val struct. So now I would say we do this by saying impl. So remember, in our previous live streams, we had done things like this, right? So if I go through when we talked about expressions, though I did not use anything that has to do with, I did not do any generic stuff, but I'm pretty sure that I did some implementation. I wrote some implementation code here, even if I did not. Let me check for other lessons. Nope. Let me see functions. How is it that I cannot see where I wrote an implementation code? It's shocking. So this is surprising, to say the least. Should have a place where I did something like that. I'm surprised that I'm surprised I can't find that. Anyways, let's move on. So basically, in a normal situation where we are not doing anything, like where we are not writing any generic code or stuff, right? So we'll just write impl, then we'll write our gen val. So we're implementing, on the gen val, right, on the struct. So this would enable us to write functions or futures, or define specific behaviors for our struct, right? So that's basically what the implementation keyword helps us to do. But in this case, right, since we are trying to make everything generic, so we can pass any type, either an integer, a boolean, a string, or a character type. We're going to make it generic, right? So in a different situation whereby we are not writing generic functions, every place where you see an angle bracket and a t is not going to be available, right? We'll be passing actual data types. So I'm going to, for the sake of clarity, I'm going to write the two different instances to just show the example. So the first one, we're going to start with the first one, which is generic type. So first we'll pass generic type for the t implementation, then we'll say gen val. So we'll pass the gen val with the t, and here we'll write a function. This function is going to be called fn. We're going to create a function called value, and this value function is going to take, as usual, reference. Going to take self, reference to self, and it is going to return whatever it is that is our generic type. So if the generic type is a boolean that we passed in, it's going to return that, right? So we're going to pass t here. So that is the placeholder, and we're going to pass the reference to self.gen. So self.gen is this, right? So self like the struct itself, talking to itself, like, right? If you're coming from JavaScript, it's kind of similar to like the this keyword, right? So we just say self.gen val, right? So this is basically how we write a generic function. But in a different situation whereby we are not doing anything that's generic, we'll do something like this. So say implement, and we'll just call it genval, right? And since we're not passing any generic, so we'll just go ahead and write our function. We'll call it value, right? And still the same thing, takes self, but in this case, we are going to maybe return, let's say, an I32, right? And yeah, so we'll go ahead and say something like reference to self gen blah blah blah, basically. So now we are not, this is not generic, right? So it would only take an I32 type, and of course our struct will also not have all this. Our struct will, instead of having t here, would have an I32 type, and will not have this angle bracket to specify that it is a generic type. So these are like, this is the difference between writing a normal implementation on a struct that does not take a generic type, and an implementation on a struct that takes a generic type, right? So the major difference here is the angle brackets. So you have one after the implementation keyword, you have another one after the struct itself, because it is an implementation of a function on a struct that defines the default behavior of that struct, right? I know this whole thing can actually be confusing, but it begins to make sense if you dwell on it, for a while. So then we have our function which defines a default behavior for this structure, right? But in this case, we are not passing a generic type. It would only ever accept an I32, right? So this was just for example's sake. So I'll just go ahead and remove this guy because we don't need that. So if you take a look at this, right, with this implementation, we can create different instances of genval. With this, we can create different instances. So I'll undo that again, just for the purpose of explanation. So with this, we can create different instances of genval with different types, such as we can create a genval of I32, we can create a genval of a string, we can create a genval of a boolean. But here we cannot do that. The only thing we can do is we can create only genvals of I32, right? So I will just comment this out and I'll add a comment. I already have this written out, so I'll just add a comment here. Um, so with this implementation, we can create instances of genval with different types, such as genval I32, genval of string, genval of a bool, because we are passing a placeholder, right? It is a placeholder. It's not like we are saying it must be an I32, right? So the value method here, this guy, so this is a function, is a method because it is an implementation of the struct. So we call it a method. It's kind of similar if you are familiar with object-oriented programming. It makes a lot of sense, right? So this is a method because it is specific to this struct, which is genval. And so the value method, this guy, will return a reference to the stored gen value, a reference to this guy, right? Regardless of whatever t is, which is whether it is an I32, a string, or a boolean. So this flexibility enables us to write reusable code that is more generic, right? It reduces redundancy, right? Helps us to write code that we can reuse in multiple places. Just like kind of like how we did here, right? We wrote one struct and used it multiple times, right? So this is an example of doing it, um, you know, implementing it for a method when we create a struct. So now let's go over to traits and how to implement traits with generics. And we are going to have like a full blown um, episode or stream that specifically speaks to traits, right? It's a big topic, it's a very big topic. But basically, traits in Rust can leverage generics to define methods that work with multiple types. So this enables us to write flexible and reusable code, right? So the entire point of this live stream is how can we write reusable code in Rust? Like, how can we make our code more generic, right? So we would create a trait called has area that calculates the area of different shapes, and we'll use that to show our example. So in order to create a trait, right, we'll use the trait keyword. So we'll say trait, and we'll say this is has area. Remember this dude calculates the area for us. So here we'll just define a function called area, and this function will take self and return an F64 or whatever. So we'll take self, return F64. So now we'll go ahead and create let's create something like, let's say, a rectangle or a circle. Let's go with a rectangle. So struct rectangle, create a rectangle. So we know that the rectangle is going to have a length and a height, right? So say length is going to be an F64, and height is going to also be an F64. So that was a mistake actually. Hold on, I saw something now. Do we now have F128? An F128 floating bit type, specifically the binary type defined in this type, is very similar to prime F32 and prime F34, but has increased precision by using twice as many bits as F64. Please see the documentation. Wow, I did not know about this. Is this a new thing? I didn't know about this. Note that no platforms have hardware to support. Oh, I see. Without enabling target specific features. As for all instruction set architectures of F128 is considered an optional feature, only Power 1 SI, blah 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 blah. Oh, I see. Okay, so let's just stick to what we. So I would definitely read up more on that. I did not know that we had an F128, and even, oh wow, even F16. I didn't know about this. I only knew about I only knew about F32s and F64. Or am I mixing it up with something else? I don't think I'm mixing up with something else. Well, okay, let's just stick to our F64, right? So X64 is supposed to be a comma, not a semicolon. So so now we have our rectangle, and we know the rectangle has length and height. So now we're going to write an implementation of our traits on our struct, the rectangle struct, right? So say implement. So guys, in case you don't really understand how the whole trait stuff works, right? We would have like a live stream that is dedicated to traits, talking about traits, where I will really dive deep and surgically explain everything, what traits are, and everything about it. But for now, let's just focus on the implementation and how we can use it um, in our code. All right, so let's move on. Okay. Hold on. Okay. Okay. So let's continue. So now we have our implementation block here. So we're going to go ahead and say, okay, let's go ahead and zoom in. So we'll say has area, and we'll say on the rectangle there we'll write our function. So we'll say fn area. Okay. So take a reference to self, and this will return an F64. And so what we'll do here is we'll just do self. Okay, F64. What have I done? Okay. So we'll do self dot length. So multiply it by self dot height. And yeah, so this is basically how, you know, this is basically how we can implement traits on a rectangle, right? We can implement a trait and use it on our rectangle, right? But now this is not generic at all. This would only accept a type of F64, right? If we try to pass any other type to this, everything will break. So in other words, how the question now lies on how do we make this generic such that the hash area can accept any type, right? That is not an F64, right? How do we make it generic such that it works for such situation? And what we can do here is, first off, every place we see an F64, we can go ahead and replace it. Then we can go ahead and specifically add our angle brackets and our placeholders. So for this to have F64, I will just um, you know, do this and I would change this to T, right? So what I did was capital letter T, right? So what I did, I just you know, highlighted all of them at once and I changed it to T. So here we have hash straight, so we need our angle brackets here. It's capital letter T. For our structs here, we also do that. We also need that, similar to how we have been doing it, right? Then in our implementation block, for where we have the implementation keyword, we'll do that here. After hash area, we'll also do that. And after our rectangle, so also do that, right? Also do that here. So automatically, we have made our implementation here, right, generic. So the reason I did that first implementation was to show you how we would write it, how we would actually write it if we are not right, if we did not want to make it generic, right? So that is how we would have done it. So now we've now gone ahead to you know, we've gone ahead to make the hash area trait you know, to work with, you know, multiple types, you know, thereby demonstrating the power of generics in Rust. So we can then go ahead, right, to, you know, further um, we can go ahead to further extend this, right? If you remember, initially I had said that you know, the traits would, that is the has area trait, would enable us to calculate the areas of different shapes, right? So it wouldn't really be satisfying if I just wrote um you know, for only rectangles. So let's try and write for another one. So let's try and see how we can implement the has area traits for other shapes, maybe like for a circle or maybe a triangle, without modifying the trait itself, that is this guy itself, right? Without modifying this guy. So guys, in case you are confused, right, you can always like research the use cases for this, right? For like traits and stuff, like use cases, right? But mostly, mainly, if you're familiar with polymorphism, like polymorphic code, this whole thing begins to make sense. Like I said in the past, once again, object-oriented programming, right? If you're familiar with it, most of these things begins to make sense. But let me just go ahead and do that for a second, right? So we'll create another, so I'll do it here, another struct called second struct. I'll call this second. So guys, always take note of how the struct starts with capital letter, right? So it has to. So that's like the convention. So we'll pass the generic type of angle brackets and a placeholder alphabet, in this case T, and we just want to find the radius. So in this case, we want to find the radius of a circle, and we want to return an F64. So guys, take note that X64 are floating point numbers, right? So any place you see something like 1.0, 3.5, anything that has a floating point, so point is an F64 in programming. So now we have our radius. So what we'll now do here is we'll now go ahead and do this similar thing, but for a circle in this case, right? So what we'll do here is I will just copy this guy. So for the sake of time, and I'll paste it here. So everything remains the same. The only thing that changes here is this. So we'll now change this to a circle. So call this a circle, right? And here we want to calculate the area, right? So what we'll do, so we know that we have like a different way of calculating the area of a circle. So that's what we are going to apply here. So first off, we'll do so std f64, and I'll say const ai, so multiplied by the self dot reduce multiplied by the self dot is multiplied by itself. So self dot reduce. So we have, as you can see, reduce, um, multiply it by self reduce. So you can immediately see how it only refers to this circle, right? Because it's only the radius that I have here. Unlike rectangle where I had access to length and height, and we did that calculation here, right, for calculating the area. So here we have also gone ahead to calculate the area of our circle, right, using the same has area trait without even touching it, right? So in this case now, in this particular implementation would work for um any integer type whatsoever, right? If it is a normal number, if it is a floating type, it would work. In my previous implementation, it would have only worked for a floating type, which is anything that is, 1 point, 1.0, 1.10, 1 point something, right? But in this case, it will work for both numbers, right? And both, you know, floating points, numbers and all that. Why am I getting mismatched type? Cannot multiply t by t. Oh, okay, I see. Hmm. Consider restricting type parameter std ops. Oh, I see. So there are some things I need to like. I think I did it in my previous stream, where I added all these. I got the multiplication, this thing from the standard library and all that. But I will not be doing that today. Not today. Not today at all. So it also says type parameter t is never used. Consider removing t, referring to it in a field, or use a marker or phantom data type, all these things. So we're going to also talk about phantom data types, right? But yeah, this is basically how we would do it. For the sake of time, I wouldn't really go deep into trying to resolve all these things because it is going to, believe me, it's going to take a lot of time. This particular multiplication stuff, so this is std ops multiplication. So it's going to specifically state that we are restricting the generic type to to be able, so we can be able to multiply, because of course you cannot multiply placeholders, right? So that's why we're having these errors here. Also, what does it say? Mismatch type parameter t, found type of f64. Okay, so that should be coming from here. That's like a typo, so I'll change this to t, and I think that error should be gone. I'm waiting for it. Let's see what happens after it finishes loading. All right, so while I'm waiting for that to load, we'll go ahead and also look at how to use multiple bounds, right? So in Rust, you can apply multiple bounds to a type using the plus symbol. So okay, so you can automatically see that that error had gone, right? Yeah, so that error had gone for. So the only thing we have now is the multiplying of t, which makes sense. You cannot multiply t, but like I said, this is something I had done in our previous streams, where I got from the standard library, got the multiplication, this guy, and I used it somehow to prevent this error, thereby stating that we should be able to multiply t, right? So that can be done, but I wouldn't be doing that, right? If you're interested in doing that, you can take your time to make a research on the std ops whatever stuff, and it would it's pretty much easy. It's very easy to do, right? Okay, so now let's look at bounds. So in Rust, you can apply multiple bounds to a type using the plus symbol. So an example of this, let's add the comments. to using multiple bounds. Okay. All right. So now let's say an example of this would be so a print debug, right? So I'll write a function that does this. I'll say function capital letter. So fn. I'll call it print underscore debug, and okay, it's going to be a generic type because what's happening here, right? And mm, let's just leave it like this for now, right? And here I would pass t, which is the arguments and a reference to generic type t, and I will try to print. So if I do print line, um, okay, we'll pass this to the debug representation and opacity, right? So then I would also pass the display representation. So this will be the display. So display does not have any of those weird stuff. So something like this. We have our semicolon, semicolon, save, right? So if I save this, um, hopefully I should get an error. I think so. I should get an error. So I'll comment these guys out for the sake of um, moving forward, right? So I'll comment this out. Otherwise, this guy's cargo check is so slow today. Um, all right. All right. So you can already see that we have this an error here saying the T doesn't implement the debug type. So this is a debug, right? It doesn't implement the debug trait. Doesn't implement that. So cannot be formatted using this because it doesn't implement debug, right? Also, we have here where it says T doesn't implement the display, right? So I mentioned I said something about display formats and strings. You may be able to use this guy or this guy for pretty prints, right? So in order for us to resolve this issue, so like I said, in Rust, we can apply multiple bounds to a type using the plus symbol, right? So for our generic, what we are going to do here is we are going to pass the debug. So we'll say debug. Then we'll use a plus and pass in our display. What's happening? Okay, so use this. Yeah, so use fmt derived org. Okay, so here we have use std fmt debug. All right, so with that, come down here and we save. So with that, we don't have, okay, print debug, not debug. Okay, so you can see that we don't have those errors again, right? So we've passed in multiple bounds using a plus symbol in this case. So like I said, the function requires the T to implement both debug and display traits, right? So we can do this using the plus symbol. This is very useful when you know when bounds become complex or when the type parameter need different constraints, right? We can do it this way. Now let's take a look at okay. Okay. All right. Yeah, so I'll just reduce the errors to the barest minimum. So next, we're going to talk about phantom types. We're going to talk about phantom types. This is not something that a lot of people talk about in the language. It's not something that you get to use every day. I just felt it was important to add it in the stream. I would have actually just ignored it and moved on. But yeah. So a phantom type is a type that does not have any direct runtime representation, right? So instead, it exists solely for the purpose of type checking, right? So it does not have any runtime presentation. So an example of this is, let's say, we get it from the use std, so marker. So there we have our phantom data, right? So if we even read this, right, it says adding phantom data field to your type tells the compiler that your type acts as though it stores a value of t, right? That is a generic placeholder, even though it doesn't really. This information is used when computing certain safety properties. For more in-depth explanation of how to use phantom type, see the Nomicon, right? So it goes on to explain and explain and explain, right? But you can always, even it gives an example of how it was used with the struct and so on and so forth, right? Yeah, so phantom data types, right? So going to phantom data, on like this here. So we can create a struct, right? So let's create a struct. So struct, I'll call it phantom, phantom tuple, right? And it's going to take generic type A and also B. So now one of them is going to be an actual value, which is A, and the second one is going to be a phantom type, which is going to wrap. So phantom is going to wrap B, which is the second one. So we'll say phantom data, and in here I will just pass my B, right? And I'll pass my semicolon, and that should be it. So in this example, right, a phantom tuple, which is this, right, is a struct that has two type parameters, like I mentioned, A and B. While A is stored as a value, B is only tracked at compile time using phantom data wrapped in B, right? Using this. So we only track this at compile time. So this particular stuff allows the compiler to enforce type constraints on B, right? Without allocating memory for it. So I'm going to add that as a comment. Right. So I already wrote that somewhere. Here. Right. So this allows the compiler to enforce type constraints on B without allocating any memory for it. Some of the use cases of this is unit tracking. Right. So phantom types can be used to track units such as measurements, meters, seconds, and stuff. Right. Another thing again is that they can help us to distinguish between different kinds of data in a type safe way. So data distinction. Right. So I would show an example of this, right? We'll write a code to show this example. By leveraging phantom types, um, you can write way more expressive code that is type safe and efficient and both maintainable, right? So let's look at some example of testing phantom types usage with units. Phantom types are, very useful, like I said, for unit conversions, where we want to ensure that different unit types cannot be combined incorrectly. So we'll create a struct called length that uses a phantom type to represent units, right? So first of all, we'll start with creating an enum. So in case you've not heard of an enum, in my previous live streams, I talked about enums in Rust. So you can go back to them or go back to the documentation and understand what enums are, but they are similar to structs, but they are not, they are actually different. So in this case, we are going to um, example of testing a phantom type with units. So we're going to look at that right now. So I'll add a comment for this here. So some examples of testing phantom data type Usage with units. Okay. So first thing we are going to do, we are going to create an enum, two enums called inch and millimeter, So I'll say enum. I'll call this inch. Just going to be an empty object. The next one is going to be enum mn, and it is also going to call an empty stuff. I'll just keep it like this for now. Okay. So now we let's move on. So let's create our struct. So we'll come back to those two guys. So we'll create our struct. Like I said, we're going to call it length. Capital letter L T N. Capital letter LENGHT. I'm going to pass our unit to it. So we'll call it units. This unit is going to act as generic, and it will take an F64 and a phantom data type. So phantom data, and that phantom data is going to take our units. Okay, so after that we need our curly semicolon. So now we're going to write an implementation. We're going to write an implementation for our length, right? We're going to write an implementation for our length. Okay. 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 So we are going to write. So we already wrote our. So we already wrote our. What's it called? Our struct. So we are going to write an implementation for that struct. But first, we're going to write a trait, and this trait is going to be called add, right? So we are going to write an implementation of our add trait on the length, right? So let's just quickly do that. So we say traits, and we'll call it add, and it takes let's say the average is the right hand side, which is going to be equals to self. So here we'll do this. So we'll have our type output. Let's call it output. So all this will make sense. And then we'll write our function. So the function is going to be add. Um, it's going to be add, and it's going to take self and the RHS. RHS. All right. Okay. So now we're going to write. Okay. So now we're going to write the implementation for this, right? Okay. Instead of doing it this way, I think I'll just go ahead and instead of writing a trait for this, I'll just go ahead and write the implementation directly. So I'll say implement. No, sorry, that's. Instead of doing this, let's just Move this one. So here I'll just draw implements and I'll pass the units. Right, so this units I'll now do our add for the length struct. I'm going to also take the units, right, and we're going to say our type typ. We're going to have an output of the length of the units exactly. So length is going to be that, and we'll have our associated function. So we add. Okay, so this our function is going to take self, similar to what we had done before. So to the right hand side, so RHS, we're going to take the units and the length and the units. So length, units, and we're going to return that. So we're going to return that. So that's generic length units, right? Then our normal curly braces. Then we're going to say length in a tuple. We're going to say self. Oh, okay, and followed by so self plus the right hand side, which is O. Then we'll pass our phantom data here. Right, phantom data, whatever it is, phantom data is. Okay, expected two arguments, found three. Oh, I did this twice. So I'm going to delete this guy. All right, have I done again? Okay, so this, right. So by using phantom types, we here we've ensured that different units, right? So different units, which is in this case, okay, cannot find the traits, the scope. So we have to add our traits scope. Um, okay, so we had initially done that here, so add it here again. That should cannot find trait. Save this. Yeah, so that resolves our issue. So this was the initial trait we wrote. So yeah, so we have our traits, we have our struct and stuff. But the main thing to take note of here is that by using the phantom types, right, we have ensured that different units, in this case, which is the inch and the millimeter, cannot be added together, right? We can't add them together, right? That's basically what we've ensured here. And we cannot add these two guys together, even if they might have the same value. The compiler also would prevent errors at compile time, right? So at compile time, the compiler will help us to prevent errors. This approach promotes type safety and prevents common errors in units, especially in unit conversions. So next, we are going to talk about new type idioms, right? So this is one of my, I would say, silent favorites of, you know, so one of my very favorite aspects. So the new type idioms is a powerful technique in Rust for creating new types that wrap existing types. So it's a very simple concept. A new type will wrap an existing type, providing compile time guarantees for safety, for type safety and preventing errors. So some of the benefits of this is that we can create new distinct types by wrapping existing ones, preventing accidental misuse of our types. Another one again is explicit conversions, whereby we add methods for explicit conversion between types, making the code more readable and maintainable. Another one again we can also think of is improved code organizations, because now we can group related functionality and behavior into the new type, right? So let's look at an example of this. So let's say we we have a struct, right, of years and days, and we know that they are all going to be of type I64, right? We cannot just say something. We cannot just do something like this. Let's say struct. I will say years. I'll just do something like this and say yes, and say 64. What am I doing? Okay. I64, right? We can't just do something like this. We can actually do this, right? But okay. Yeah, okay. So what we did here is instead of so basically we are wrapping this type with year, right? We also do the same thing because now we know that we want another struct that has the same type, right? So we'll say struct days, so call these days. So wrap it with an I64, right? So now we can go ahead and implement years, right? So basically we can go ahead and write an implementation for this. So we can say implement. What's happening? Years. Implement years. And in there we create a function. So we'll create a function today's. So call it today's. So basically today's, I'll take a reference to self. And we're going to return days, right? And in there we'll just say days. We'll just multiply it by self.0 multiplied by 365. So self divided by 365, which is number of days in a year. 365. Right. So in this example, we've created years and days type. Right. So this is what we did here. We've created the years and days type, providing an explicit conversion method, which is today's, right? So an explicit conversion method that ensures that the year and days are distinct types, right? So this was with I64, not I63, to ensure that they are distinct types, and also ensures that conversion between these two guys are explicit and safe, right? So by applying new type idioms, you can make code more expressive, type safe, and maintainable, right? Um, yeah. So last but not the least, we're going to look at um, associated types in Rust. So in Rust, associated types enables you to define types within traits without requiring explicit specification all the time. This feature once again promotes, cleaner and more concise codes. So associated types can, reduce code duplication or code repetition, making your code more efficient and easy to maintain by others. So let's quickly look at an example without taking much time. So I'll add a comment for this to make it easier for us to differentiate associated types. So first off, we'll create a trait, right? We'll create a trait that we'll call contains. This trait would have two types and a method to itself, right? So let's just go ahead and do that. So we'll say traits, and we'll call it contains. So we have type here, call this type A. Have type B, and then we'll have our function. So call our function contains, and this function is going to take a reference to itself, so self, and we're going to pass A, which is also a reference to self dot A, reference to self A, and we're going to have B, which is also almost similar. So it's going to take a reference to self B. It's going to return a boolean. And this boolean is going to now take the So it's just going to return a boolean, right? So it's just our trait. So you know that it returns either true or false. So other, this is traits, not traits. Okay, yeah. So that's that. So next we are going to define our struct. So struct, on this struct we are going to call it, what's happening to me today? I'm going to call it container. Container. And this container is going to take data. So the data is going to be a vector of i32s. So call it a vec. I'm going to pass our i32 here. Okay. Comma. Nice. So now we are now going to implement our traits on our struct container. So we're going to write an implementation for that. So we'll say impl. So take note, this is not a generic one. We're just writing normal stuff to show associated types. So this is contains for container. So for container, right? So in here, we're now going to define our, is it contains? Yes, not all traits implemented. Oh, okay. So it's telling us that not all traits item implemented. So it's telling us that the type A, type B, and the contains function is missing. So we'll definitely add that. In fact, that's why we are here. So we'll say type A. So type A will make it a type of I32, right? Then we'll add our semicolon. Don't ever forget the semicolon. Next, we'll still have that same error, right? Now you can see that we are no longer seeing type A, so it's not type B and the function fn contains. So I'm going to do that with type B. Also going to make it a type of I32, right? Now we only have fn contains missing. So now we're going to write our function on this space, or our method, sorry, that is the right word to use. I'll call it contains. So it takes, as usual, self, right? So a reference to itself. The reason we are passing the reference is because we don't want to completely and entirely copy or take ownership of, you know, that value. So we have to pass a reference. If you completely take ownership of that value, we would have issues with the compiler. So the next value is A. So it's going to also take, a reference to self. And yeah, from self, we want to get A, right? So self in this case to get A. What's happening? I don't know what's happening to me today. I'm just making a lot of typos. So next is B, and we're going to also take a reference to self and B. I think just do the shortcut. So yeah, so bool, right? So in here, fn contains is not a member of the tree. It contains, wrong spelling. So I'll just copy this and place it here. Yeah, so that's correct now. All right. So in here, we then want to do some kind of like basic level comparison, right? So a very simple comparison. So I want to say self dot data. So the data is coming from our struct dot contains. We know that our struct, the data in our struct is a vector, and on the vector we have a contains method that checks for if the vector is like an array that checks if the vector contains a particular element. So we're going to pass A. Remember, A is what we are getting from our trait, So we'll say if it contains, so say contains. So you can immediately, so yeah, contains A. Then I want to so the and operator, so and if self the data contains B, right? So we just want to do like a simple level content. So if I hover over this and we read through what we have from the Rust analyzer, so we can see that this is a vector, right? So it's kind of like an array if you're coming from languages like JavaScript, right? So you can see that here something like this was declared, which is let v equals to 10, 40, 30, right? So here they are asserting and saying if v contains, a reference to 30. So like I said, we don't want to take ownership of that value. Of course, it doesn't belong to us, right? And so we have to pass a reference, like something like on a lower level, that kind of like a pointer pointing to somewhere in memory saying, okay, I know I don't own this data, but I can refer you to the guy that owns this data so that you can have reference to that data. So that's basically what this whole thing means, right? It's kind of it can be confusing sometimes, but when you go into ownership and borrowing in Rust, it begins to make a lot of sense why language was designed this way. So basically here we are checking if it contains that 30, right? So if it contains 30, we get a boolean response, either true or false. Here checking if it does not. So that's why we have that exclamation mark before the V here. I think it contains V and V. Of course, we know that it does not contain 50. Right. So this is like an example usage. So we can also make use of it with I guess we can also make use of contains um with strings. I'm not sure. But basically, this is an example implementation of it. So in order to test this, I know we've not run any code today. It has been a lot of explanations and explanations and explanations, right? I'm going to try as much as possible. I'm going to try my best to kind of pass some values and see how we can use it, right? So in our generic function here, so I'm going to make this guy public so that I can use him in our main file. So I'm going to pub. So it's now exposed to the outside world. And here, down here, I'll just put associated types. Command V. Okay, associated types. And so now first thing I'm going to do is the container, right? So I know the container, the struct itself, I have to pass data into it. Remember, I said it is a vector of I32, so it's expecting numbers, right? So I have to pass a vector to it. So how do I do that? The first thing I do, I have to initialize it, right? So I can say container. So if I write container, I see there are options here. So I can go over those options. And then I get to this, then I click on container. If I hover over this, you see it references the structs that I had initially defined somewhere here, right? So everything is linked, right? So that container has an object, so similar to how it is here, right? And it then has a data and a vector of I32. So I'll follow that same format, right? Nothing too serious. And I'll create a vector. So using the vector macro. And in here I'll pass 1, 2, 3, 4, right? And finally 5, right? So we have this. So we've passed our value here. And so with this, we've initialized values in our container struct. Right? So in order for us to be able to use it, we have to then append it to a variable. So we'll say let's container be equals to this. So there will be like a kind of like an implicit inference here for us. So let me save. Telling us that this is a vector, right, of integers. So we'd have something like, why am I having this error? Okay, I need like a semicolon, but okay. Yeah, so we have the container. So okay, it's inferred our container, right? And that makes a lot of sense because it would only infer a vector if we're actually passing a vector directly. But if I do that in this case, I'll have an error because it is expecting I think the structure of a struct, right? So it doesn't hurt to test that, right? So first off, I'll add my semicolon to get rid of this error. Then what I would do is I would cut this out. So I'll just delete some things. So I just want to break this code a little bit and test stuff and see, right, what happens. Like, what's the worst that can happen, right? So let's just do this and see what happens. Okay, so you can see, yeah. So in this case, because I directly passed the vector, so I'll pass my semicolon here. So because I directly passed the vector, it would infer a vector type of I32, right? Yeah, that's what would happen here, right? So, but that is not what we need in this case, right? Because we want to initialize our struct container struct. So we'll just undo this and get it back to what we had it before. So we'll bring it back to this place, and I'll save this. Okay. Yeah, so our error is gone. I don't know why my cargo check is slow today, so it takes time. But yeah, with this we've initialized. Don't mind the warning that you see here, is because we've not used the container. We're going to use that shortly, right? So now, So how do we go ahead to use this, right? So um, we do like a very simple print, right? So what we want to do, we'll pass some reference, some numbers, and we'll expect a boolean. Remember, what we are returning from in our struct, what we expect to be returned from our struct is a boolean, right? And we in our traits, and in our traits we defined a function that we called contains, right? And this function takes a reference to itself, a reference to the type of A, and a reference to the type of B, right? So the self is kind of referring to itself in this case, right? So at the end of the day, we want to return a boolean, true or false. So we then went ahead to use that type in the implementation we did on our structs using our traits, right? It can be kind of confusing sometimes, but you know, you do this for some time, it begins to make a lot of sense. So here in our implementation, where we implemented our traits on our struct container, we then defined our types. So type A, type B, I32s, and we then created our function that just similar to this guy here, right? Similar to the guy in our traits, but here we're now doing our, check, because now we now have access to a vector. So because we have access to vector, we can now do self, which is the struct, dot data, which is the child that is in it, right? So which is this guy, dot contains, because data in this case is now a vector, right? So if it contains the value that will be passing into our contains function, right? So I'm talking too much, so let me just go ahead and do the final implementation. So here I'll write some print statements. I'll say print line. Um, guys, forgive me, I'm lazy today. Just try as much as possible to. So now I will say container. So remember, we have this guy that is unused, right? And this guy is, you know, our struct itself. And through our struct, we have access to contains, right? Through our struct, we have access to contains because we have written the trait implementation of contains on our struct, right? So we can now say container dot. So if we do that, it should suggest to us. So we have data, you can see data. On that, we also have contains, right? So we can say container dot contains, and this guy expects two values, right? Because remember A and B, right? We are passing A and B into the function, contains function. Forget about the self, right? So the first one we're going to pass a reference, so it has to be a reference. So reference of 3, and because we know we have 3 in our vector, right? We have 3 in this place where we defined our kind of like an array in JavaScript, and we're going to also pass reference to 5. All right. So that's for this. So our output here should be true. Let's do another one for false. Print. So we'll say print line. Okay. So we'll have curly brackets. And here we'll just say contains. And I'll pass 10 and reference to another one. I'll pass 20 because we know we don't have those guys in our stuff, right? So yeah, so that's basically it, right? That we are basically done here. So I'll just comment out the rest of these guys because I don't want errors, something that will break the code, prevents us from seeing the values that we are looking for. So save this. All right. Okay. So this will still not work, right? Unless we go ahead and use the public function in our main function. Right. So now that we've saved this, we'll now go to our main function. So here, okay, so we'll then call our generic. So we have access to that function, and cannot find struct test. Hmm. Am I having okay? Save this. So if I hover over this, you can see the function, the generic function, right, from that other module. So you can see all the things we had in that function. So it's exposed and is available in the main function. So you take a look at this guy, you can see all these things here. All right, so let's go ahead and cargo run and see what happens. This is the first time I'm running cargo run since today. Today's stream is kind of weird. Okay, so it's building. All right. Still building. I think this is a little bit zoomed in too much. So let me zoom out. Okay. Okay. So if you take a look now, you can then see that we have true, false, right? You can see we have true, false here, right? So if we go back to our implementation, close this guy. Don't need him to be open. So if we go back to this place, you see that we are doing some checks, right? So we are saying container.contains, which is the function that we wrote. So we want you to check using the contains method that comes from our vector, right? So we can further validate and confirm this by I think I have so contains Rust vec. So I have a somewhere I researched that, so I would just quickly pull that down for us to take a look. So this is it, the vec std. How do I check for things in vector? So this is a Stack Overflow question someone asked. So just open that in another tab. So we have the best way to call vec contains in this case. Okay, how to check the string exists in a vector. Contains search. So let's look at this. All right, so let's search. So we have std hash sets contains. This is hash sets, hash sets, hash sets, hash sets. Nope. Let me look at this. So we have okay. So someone said. So basically, you can see it here, right? So let's vec. So this is our vector macro that has a string of I minus I and mmm. So if n contains the reference to this guy, print yes, else no. So this basically like this is someone's Stack Overflow question, right? But you kind of get the idea, right? Of how and why we can use contains and why we were able to do that comparison is because we declared a vector here, right? So this vector, and on this vector, we are able to get access to a method that enables us to compare two things, to compare if these values that we passed into our function, which is the contains function, right? If it is available. So these are our contains function, right? The one we wrote, we implemented the one we implemented on our struct using our traits that we had initially defined. So guys, I could go on and on and on and continue explaining this stuff, but we will not leave this place today. But basically, this stream is going to almost 2 hours. And yeah, so that's basically it for generics in Rust. Generics in Rust, provides a powerful way for us to write very flexible code that is type safe and efficient. By using type parameters, bounds, and associated types, you can write highly reusable and safe code that works with a wide range of data type. You can also create, highly reusable safe code that works with data types without sacrificing performance, which is very important. So I also looked at advanced concepts like phantom types, even if I know I didn't do much justice into explaining it, and also new type idioms, to help you build more structured and maintainable code, right? So by mastering and understanding generics, you'll be able to write more expressive and usable code, enabling you to handle more complex problems with ease. So guys, thank you so much for joining me on this live stream, and I will see you in the next one. Bye.